side is infinite degree of freedom object. On the right hand side, this is a single parameter. There's no way you can do it, only if the field is gauged. Then I can select Ni to cancel this factor. So I think this is the that means given any spatial matrix, God is so clever. So you know that if you put force calculate the determinants, that you still get infinite degree of freedom. There's no way you can integrate the equation. Although Schrodinger equation written down, but that Schrodinger equation is useless. You cannot really calculate anything because it's path dependent. So, but however, the miracle is for any vector or so-called Hodge decomposition, for any vector, I can decompose this vector into divergent plus a curl and then plus a invariant object, and then this delta object is the invariant object, and then this part can be gauged away. I mean, this is the gauge. This is why the answer to why the world is being gauged. So now if you after you collapse this, then your Schrodinger equation will be a total integral. Or your Schrodinger equation will become as simple as this. And then you can prove that then the evolution operator is really in superspace, which is technical. I don't want to. I'm serious over time, so I don't want to come in. But what I'm going to say is, this is infinite degree of freedom object is collapsed into a what? Into a single parameter to become your time. This time is intrinsic, not given from outside. It's once the initial data is given to you, you know what it is. Or once the universe is birth, then you know what it is. Then everything will be evolved quantum mechanically with this time. And then you can correspond, then you can guarantee, for example, you can, and then because, and the more important is because we are talking about field theory. The Hamiltonian depends on time and therefore do not commute at different time. Then you have to do what? You have to do a time ordering. So that means even without a light cone, without any subsidiary any other input information, I know that causal order must exist because of the very structure of quantum field theory. You have the causal order, and this causal order, because H is gauge invariant object, then this causal order is gauge invariant. There is no way you can do coordinate transformation to reverse the order. Even God cannot do it. So I think causality is an outcome of quantum field theory, and it's proved by the integrability of the Schrodinger equation. So I think this is more fundamental. By saying that causality is because of the background produce a light cone, and the light cone tell you how things should change within the time-like region. And then the problem is, what about outside time-like region? So the whole problem is not whether the speed of light is infinite or finite or whatsoever. The important point is the causal order is coming from the nature of quantum field theory. So that means, come to this point, you're in the correct way, because basically you have to use every property of quantum field theory to achieve what you have to achieve. So let me come to my conclusion. Four-dimensional diffeomorphism invariant is an accidental symmetry in Einstein GR. And gravitational theory only bears three-dimensional diffeomorphism invariant. The correct question to ask about gravitation is how to evolve the initial data by a local Hamiltonian density. Not to ask and what are the general solutions. Those are questions that has been wasting people so much time in it. The correct Hamiltonian can be obtained by the generalized dispersion relation. For example, EU p squared plus m to particle to field theory, which is g bar bar plus v. The v is the most general v, include the Ritchie curvature, free Ritchie curvature, and also dimension 6 quantum operator, blah 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 things. And intrinsic time is a geometrical invariant delta H. The world has to be gauged because we have to have time. Now, more important, actually the Hamiltonian general equation motion, the equation motion actually generates correct VPE relation. You know, in special relativity, in order to include massless particle, the velocity of a particle is not mv. In order to include massless particle, the velocity and momentum relation is like this. It's v equal to p over e c squared. And this relation actually is the only relation, if you work out, is compatible with particle wave duality. And then because of our square root Hamiltonian, you can see that then the velocity p relation, this moment p is my momentum, this is velocity, and this is energy. That satisfy this spirit, and therefore satisfy the particle wave duality. And one can show that with a quadratic potential like this, including the quantum tensor, then you have a non-perturbative consistent and perturbative renormalizable theory. So although I haven't proved that there's no singularity, but I suspect that at the end of the day I can prove that to you, to George, maybe a few years later, there will be no singularity. Yeah, because it's obvious, at least it's dimension counting, and this is renormalizable. So, the last transparent. So, phi d di and general and Einstein general relativity deliver same on-cell physical content, but with fundamental different physics, physics. So we have a completely gauged universe with renormalizability and unitary illusion extension. Thank you.
For everybody who stayed on behalf of the speaker. So only urgent question. Anybody can come forth and discuss with the speaker. Okay. So you have some urgent questions you may have. I have one urgent question.
You mentioned this. Okay, in quantum mechanics, you not only you have Schrodinger equation, but you also have basic fundamental commutation relation, right? But that commutation relation can be changed or keep invariant by canonical transform. Right? Yeah. And that canonical transform does not affect the time we used to know, the textbook time.
Yeah.
Now you have a non-textbook time, the log Q, right?
Yeah.
So what does that change the picture? I mean, your time now depends on your coordinate Q, and how that changes after canonical transformation.
In the sense, canonical transformation in this is two types. One is coordinate transformation, and other is relation between field transformation. And that canonical transformation, that means do not alter the Poisson bracket. The spirit of canonical transformation is not alter the Poisson bracket.
Okay.
And the equation motion is given by Poisson bracket. X dot is equal to X. Poisson bracket between X and H. So that won't change. More important is H actually is a gauge invariant object as proved because of the Hodge decomposition. It's gauge invariant. It doesn't matter how you change it for coordinate whatever. Yeah.
So I want to come back to a very basic. I think on behalf of everybody, starting from page 10, nobody can follow because it's so condensed.
I'm sorry.
And it doesn't matter whether we trust you or not.
Yeah.
But at the end of the day, it's usually said, saying that at the Planck scale, we have a deep problem for gravity in the particle physics context.
Yeah.
So do you have any insight at the end of the day on the Planck scale problem? That gravity becomes strong and nobody knows how to handle it. You think that this can really resolve that problem? Whereas string theory, also, there was one string theorist and he has left, so I was hoping he would defend his territory.
Okay. Okay, I think the correct physics is, for example, my potential. The important role of this theory is my Hamiltonian is like this, and these are h dependent, time dependent objects. And at various time, different terms will dominate. For example, at very early universe, this is a dimension 6, so-called dimension 6 quantum tensor. At very early universe means that earlier than prime time. One can show that this will be the dominating term in your potential. Okay. Now, if you work out the detail, for example, work out the detail for Bianchi type, I forget whether it's type 1 or type 6 model, one can show that explicitly there will be no singularity at all. It becomes a simple harmonic oscillator. Well, certainly you will say, well, this is just a particular model. I don't have to trust you. But however, this is another way to see it is this is power counting renormalizable because it's dimension 6 operator. So that's another way to see it. But an explicit calculation on Bianchi type model, then this is really fine. This dominating term will really give you singularity free universe. For FRW model, it's a little bit complicated. And since I don't want to introduce so many technicalities, for FRW model, singularity is still there, but I'm quite sure we can get rid of it. There's no problem. Yeah. So, but an explicit example is an explicit non-trivial example is Bianchi type model. That's singularity free. So that means the more important for this theory, at different stage. For example, at late stage, this dimension 6 operator, dimension 2 operator, this dimension 2 operator, this operator drops out. Only the what? Only the cosmological constant will stay. That means at late stage of the universe, is de Sitter, which is consistent with observation. Or also at early stage, actually when you plug this in, you see that at early universe, actually it's also de Sitter. That means you do not need infinite time. So that's the reason. Although inflation is a good idea, but however, to realize inflation, you don't need infinite time. Put it this way. With this operator, you can.
Is automatic?
It's automatic, yeah.
Okay. Anyway, I think okay.
You seem to come up with from Schrödinger equation and somehow collapse the infinite variable in
the single parameter.
Yeah, into a single parameter time
to become time.
Yeah, to become time, and then you somehow compare the extrinsic curvature to get the Einstein equation. But in the beginning you come from a linear equation, that's Schrödinger equation, that's quantum mechanics. You have superposition principle, and then you end up with a nonlinear equation. So how the thing come out? How the thing become consistent?
Yeah, thank you for asking this question. This is a deep question, actually.
All right.
Actually, this is a very deep question. For example, suppose a quantum theory of gravity, say loop quantum gravity, of string theory for quantum gravity. How can you guarantee you have a classical world? How do you guarantee that? They say, oh, the decoherent, blah, 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 things like this. No. Actually, it's the nonlinearity in the theory that guarantee that your theory will get a classical world. And look, this is a square root over here. Although the square root is technically very difficult. But however, this is enough. For example, Dirac equation do not, because linear in momentum. So do not have a corresponding classical world. So in order to have classical world, you have nonlinear, you have quadratic momentums to create enough nonlinearity. So you have a square root here, it's even more nonlinear. So that means this theory guarantee that you will have a what? You will have a classical world. And because of that, so it makes sense to compare. It makes sense to compare at late time with Einstein equation. Yeah.
But does that solve the Schrödinger-Cat problem?
There's no Schrödinger-Cat problem.
No Schrödinger-Cat. Okay.
I think.
Alright. So suppose you have a superposition of two black holes, or one black hole with two copies, which has occupied different coordinate space. How would that gravitational field from this superposition of black hole look like?
George must be saying, wow, how come Hoi-Lai becomes so exotic today? I mean, I tell you, there's no Schrödinger question. I mean, the ETR problem. I mean, if you use this picture, if you really believe in Hamilton-Jacobi equation, that is the nonlinearity of the development in the equation that will evoke your Schrödinger equation into a what? Into a semi-classical world. So that means there cannot be a Schrödinger cat. Schrödinger cat is a macroscopic object. The nonlinearity is spoiled already. If you believe in this Hamilton-Jacobi business, just no Schrödinger cat. Schrödinger those people. I mean, they manual people, waveform correct people, and they just confusing themselves.
Okay.
Yeah. If you believe in the Hamilton-Jacobi picture.
So you mean in the atomic scale, you do have superposition?
Yeah, sure.
But at certain boundary.
At certain scale, when the universe become bigger, then it will become semi-classical because of nonlinearity development. Then finally
how do we see in your equation this transition?
I cannot show you.
I
haven't
seen.
No, not. But how do I perceive this from your equation?
Oh, that you can
I would suggest that you guys go offline.
Okay.
These are all extremely interesting
see,
questions.
Yeah, you see, this is the Hamilton-Jacobi equation. If you write it out, there's a square root inside. It's nonlinear.
Okay.
So is this nonlinearity spoil the what? Spoil the phase coherence in the theory. Guarantee that the phase coherence spoiled.
It guarantees coherence is spoiled, but doesn't necessarily guarantee a classical world to develop.
I think that, well, if there's no phase correlation, then by definition we call it classical. Yeah.
But this is the operator equation, I thought.
Yeah, on this side is the operator equation, this is the same operator equation, yeah.
Yeah, so we are talking about different things. In the operator equation, of course, you can have nonlinearity, but your quantum state still follow superposition principle, or don't they?
Yeah.
Yeah,
That's
what I mean.
The full quantum state. If you have got over, I believe you have got overlooked our universe. I think our universe still full quantum.
Right. So in that case, you still have Schrödinger cat, right?
No, not in that sense.
Okay.
Why?
If you have to by the principle of superposition, then how can you avoid that? Even though that's an imaginary situation, it's a fictitious situation. How can you avoid that?
I can avoid it because nobody can measure the universe.
Okay.
I'm talking about the way. I mean, at this level.
Yeah, at this level.
I cannot.
but then,
I get, well,
so
I'm
your
not going to
answer
say
is
this
that
is
nobody
perfect.
can prepare the Schrodinger cat, therefore you don't need to deal with this problem.
Yeah, yeah.
Okay, because there's no foreseeable way to produce a Schrodinger cat.
Yeah.
But in the atomic scale, they already made that, right? So there's
Well, it has atomic scale, sure, you just go back to quantum
At
mechanics.
atomic scale, what is life and death?
no, but you can have an atom at two different positions, just one atom. You trap the atom trapped in the optical trap.
Oh, yeah. So that's the Schrodinger's cat problem,
Yeah.
which is not a problem at the atomic scale.
At
Right.
atomic
It's not
scale,
a
it's not a
problem.
problem.
Life and death is about irreversibility,
Yeah, that's right.
extreme of causality.
But that's not what he's talking about. That was something
No, but he's
I
saying that he guarantees there's a loss of coherence, which is basically true, but how does that really touch Schrodinger's cat? It's very complicated, you know. Anyway, let me cut it off. I think we all stayed because there are two things. One thing is it's a fascinating subject. The other one, especially for the younger people, oh, there are also smiling older people here. At least it's obvious of the enthusiasm and passion of the speaker. And this we have to really respect and try to copy. So let's thank Professor Yu again.